Right, what we're going to do in this session is try and define nub for ourselves. And remember, when I introduced the problem, I said that there were two different versions of nub. One keeps the first occurrence of any element. And we see that an example of that here. And the other example keeps the last occurrence of any element. We see an example of that here. Let's try and work with the first one first. And remember, we simply take a list to a list, and the nub of an empty list is going to be the empty list. So that's the easy case. What about the case of x cons x's? Now, what we're doing here is preserving the first occurrence of any element. So the answer, the first element of any recursion, any nub of a non-empty list will be the first element in that list. But what will be the rest? It won't be nub of x's. What we have to do is remove all the occurrences of x from x's. So let's write that. So what I'm saying here is, first remove all the x's, for every occurrence of x from x's, and then take the nub of that. Fine. And this is a nice approach to the problem. What we've done is we've said, if only we had a function remove all, then we'd be able to define it like this. But the problem is we don't have a function remove all. So in order to make the compiler happy, we could just say, the answer is x's, for example. And that would give us a definition of remove all. And then if we exported nub, we should have something which will compile. Let's just save that. And let's compile it over here. We're getting a warning that variable x is unused. Well, it is, because we've got a silly dummy definition there. But the definition does compile. But that's a silly definition. Let's change it. And let's go to try and define this properly. Well, we're going to do recursion on the list. What's remove all of everything from, all the x's from the empty list must be the empty list. But what about a list which isn't empty? Well, what could we do? Well, if we got an x at the beginning, we know what to do. We just remove it. And so we call remove all. Whoops. The answer is remove all. Remove all x from x's. Yes, because we're removing every x. We're not removing the first. If we're removing the first, we just return x's. Now the final sort of case we have is that we have x here, and we have something else here. Let's see if I get x's. What do we do in this case? Well, we know if we hit this clause, x and y are not equal. So we want to put y in our answer, but then what do we have to do for the rest of the list? We have to remove all the x's, remove every x from the tail x's. And you could imagine we could redefine this as a case. Now, you can see we're getting some wavy lines, and those indicate that we're having variables not being used, because we don't actually use x there, we can just put any value there. But we do in fact need x and y here, both x and y are needed there. Okay, well let's save this, and let's compile it, let's see what happens. Now we're getting, it has compiled okay. Now should we see what our function does? It's called where2 nub, and let's try it on this example list. Let's cut that and just paste it here, and let's see what we get. And indeed we've got that case where we have deleted all future occurrences, because what we have done is every time we meet an element, the first time we include it in the answer, and then we remove every other occurrence of it before we call nub recursively. So this is a complex recursion going on here. We are checking, we are not calling nub recursively on x's, but we remove every occurrence of x before we call nub recursively. Now what about doing the other? I'm going to call it, just to avoid confusion, I'm going to call it bun, because it's like nub but it works backwards. How are we going to define our function bun? Well, bun on an empty list will return an empty list. But what about bun on a list x cons x's? What we want to do is remove all the occurrences but the last one. So what I'm going to do is do a case switch here, depending on whether x is a member of x's. I have to think about how we're going to define that. So suppose x is a member of x's. What do we do? If x is a member of x's, then we just take bun of x's. Because we know that the thing we're looking for is in the tail. If not, what do we do? We'd better include x in the result and stick that on the front of bun of x's. So there we've got our definition. But again, I've used a function I haven't yet defined called member. Now, what I'm going to do, in fact, there is a function in the lists module called member, and I'm going to call that. And I'm going to export bun. Oops. And then this should compile happily. Let's just take a look again at what we've done. Bun of the empty list is the empty list. Bun of x cons x's. If x occurs in x's, we just take the bun of x's. Otherwise, x is the first element of the result, and the bun of x's, bun of a tail, is the remainder. Let's save that, and let's compile this. And let's see what happens when we take bun on this example. Oops. You see that we are getting the order that we expected. We're getting the last occurrence of 3 and 1. Now, just to complete and give us another example, let's have a look at member. What does member do? It takes an element and a list. So whatever the value is for an empty list, the answer is going to be false. If I have, on the other hand, an element, I'm looking for an element x, and x is the first member element of my list, the answer is true. Otherwise, I'm in the situation where the first element of my list is not equal to the thing I'm looking for. So what's the answer? Well, the only place that x could belong is in x's. So I better check whether x is a member of x's. So I can say that. Now, I'm not going to export that, but I am going to just call it here. So I've now got my own member function, which gets called. Now, I'm getting some warnings here because actually here I don't need that value at all here. And in fact here, I don't need the value. So, if it's equal to the first element, the answer is true. Otherwise, I look for x in the tail of the list. And that should, let's save that, and let's compile it again, and let's see if bun does what it should do. Yeah, we're getting the same answer there. And here we've defined our own member function. Now you can see all of these they're all examples of, if I pull this down, they're all examples of recursion over lists. But each of them has a slightly different character from the template that we saw. The template gives us a guide to getting started, but sometimes we just have to think about how the cases, particularly if there are two arguments to a function, how we deal with those cases, those two arguments together. We might have a case, a base case in one or in the other. We might have to use repeated variables to check equalities between, for example, x and the first element of the list we're looking through. And again, the strategy I used here was to define the top level function. I defined nub in terms of remove all. I defined bun in terms of member. So this strategy of thinking what's a good intermediate case, it's divide and conquer if you like. We think if only I had a function to do this, I could define the answer. So do that, and then as a second half of your solution, define the if only I had that function. And as you saw in the case of member, it actually was there inside the lists module anyway. Remove all isn't there. There's a function to remove the first occurrence of an element, but not to remove every occurrence. Okay, so I hope that gave you an overview of the sorts of things we can do with recursion on lists. We'll have one final session on this, and then you'll be able to try a whole lot of these things out for yourself in some bigger problems. Okay, but that's it for this piece of live coding. Okay, good.